Our next speaker, Pedro, is going to talk about OMPC, FPGA, integrating multi-FPGA acceleration to OpenMP distributed compute. Pedro di Francia Rosso is a PhD candidate at the Institute of Computing at Unicamp in Brazil. The focus of his research is on FPGA programming using OpenMP, providing FPGA acceleration to the OpenMP Cluster framework. Pedro holds a master's in computer science by the Federal University of ABC in Brazil, with research focus on fault tolerant for MPI. Pedro's interests are in parallel programming, accelerators, and high-performance computing.
Today I will be speaking about integrating multi-FPGA acceleration to OpenMP distributed computing. So this basically adds FPGA acceleration to OMPC, which is the OpenMP Cluster framework programming model that it's basically our main project here in our laboratory in Brazil. And this work we recently published in the last IWOMP, the workshop on OpenMP that was held in Australia in September. So for this presentation, I will do a little bit of introduction, motivation, and explain a bit of concepts more on the OpenMP side. Then I will speak about some of OpenMP offloading, OMC, and OMC FJ if someone does know yet. Then I will talk a bit about accelerating communication, how we did it in the disintegration, and how we can use our framework here to explore more heterogeneity using scenarios like CPU, CPU plus FPGA, or CPU plus FPGA plus GPUs. And then at the end, I would like to speak a little bit about what is ahead for both OMC and OMC on FPGAs. So here's a little QR code for this presentation if you want to look at it in the future. So we are here on the HACC Talks talking about heterogeneous applications. So it's become a fact that accelerators are paramount for HPC nowadays. We need to use accelerators, GPUs, FPGAs, and other things to improve the performance of our applications. And we believe FPGAs can be used for that. But on the other hand, FPGAs sometimes can require a lot of knowledge in different aspects, which is not practical, especially for the people that are developing applications for HPC but are not experts in computing. So here the side I put a little two stacks that what we calling FPGA regular stack and reduced stack, where FPGA regular stack is basically listing where you need to know basically to develop an parallel FPGA accelerated distributed applications. So you see that you need to understand a lot of things to use apart from the domain expertise in the application you're developing. And our framework tries to abstract a few things on this using only OpenMP. So I believe most of you heard about of OpenMP. OpenMP is de facto the parallel standard, parallel programming model is standard for the HPC. It's widely used, and we believe this can be the key to facilitate the use of FPGA acceleration into the HPC applications. So we believe that many aspects of this stack can be abstracted only by using OpenMP and hiding the other things under the hood, so the user does not have to worry about them. To give a bit more of motivation on this, let's say we have a very basic example here that is element-wise sum of two vectors. So we want to sum A and B into C, and we have several FPGAs. So you can think of this as any application that you can block and do some kind of spatial parallelism here. So let's say we want to block these vectors into 8 parts, and do each computation in parallel with in 8 FPGAs. And this is actually, giving a parenthesis here, this is actually the structure we have here in Unicamp. You have like 4 nodes with with 2 FPGAs each. And let's say we want to do this on the FPGA, doing a block on each FPGA. And again, this is a very basic just for you to understand. You can think of this of any other application. So if you want to program this just using a simple CPU code, parallelizing with regular OpenMP, you would end up with something like this. It's a very basic code, very simple, very small code, and we don't really need to go further in details of this code, but I just want to see the big picture here. And this is the OpenMP plus MPI plus XRT, which means that is going from the CPU version to something that is distributed using MPI, and something that is FPGA accelerated using the FPGAs here. So this is basically how that code turned in something distributed using FPGAs. And with our framework, you can achieve the same thing that we see here, only with these modifications. So you see that it's much more simpler, but you can also say that it's going to change for the type, for who is implementing, maybe implement something different here and there, but usually you're going to see a lot of reduction in the efforts to implement. So I highlighted here that the difference we have from the first code I showed. So this is the first code, let's say the baseline, and this is our framework. So you can see that we just added a few things, so you have much less effort to implement distributed FPGA acceleration than the usual way to do. Put this in numbers. Here are some Halstead metrics. So for those who doesn't know, Halstead metrics are metrics that evaluate complexity code, not code complexity. So basically here we are measuring the effort to implement code. And there are several metrics here that are taken from the number of operators and operands you have in our code. But basically, I would call the attention for the efforts to implement and time to implement that are two equivalent metrics. Basically, they are they have a relationship that they kind of represent the same thing. But you can see that for that very basic code that I showed, the regular stack is roughly 3 times higher than the baseline. So you can imagine that takes 3 times more time to implement than the baseline. And the reduced stack is only 11 times higher than the baseline. So it would take much more time than the baseline to implement. So this is what we're trying to do. We abstracting and facilitating the development of applications, providing a framework that is easier to do FPGA acceleration. Okay, say that. Let's talk a bit about OpenMP offloading. So the OpenMP standard, the program model is huge. That's a lot of things, but that is a very small part of OpenMP that's called OpenMP offloading. So OpenMP was idealized for shared memory parallelization in the CPUs, and the OpenMP offloading brings the idea of taking the computation to another device. So you can think like taking computation to a CPU, or taking computation to a GPU, or in our case, taking the computation to an FPGA by only using OpenMP, right? So the basic idea is that we have a few directives. For those who doesn't know, OpenMP is a directive program model where you specify the directives to say how it should parallelize your program. And that is a very few directives that are the target directives that focus on these devices. So targets you can understand as other devices that can be CPUs, GPUs, FPGAs, and all those things. And basically the idea is that whenever you have a target directive, it means that the following, here we have this function. So this function will be compiled for a given device. So if you compile this code targeting CPU, it's going to compile this function that is the target code to the CPU device. If you compile this targeting the AMD GPU's architecture, it's going to compile for this function for something that AMD GPUs can understand and execute and generate the results we have. So that's the basic idea. You have a simple code that you can offload for different devices using targeting the architectures on the compile time. OMP Cluster, OMPC, that is our basic project, brings the idea of devices to nodes, because the original OpenMP target idea is to offload the computation to devices in the same node. So you execute your code on your server, and if the server has GPUs, you can use the GPUs. You have other things, you can use the other things, but for a single node one. So OMPC will bring this idea of the device can be a node in a cluster. So we expanded this to something that's actually distributed. So the basic architecture of OpenMP offloading is to you program your code using the target directives, and it will generate some device code that is code for the architecture you choose during the compile time, and some host code to control the application execution. And then you have the target runtime part that takes that code and executes in the devices you have. So it's basically composed by two APIs here. So you have the agnostic layer, basically, that is the layer that controls data movement, data mapping, and all those things across the devices you have. So it's agnostic of the device in the sense that it not controls anything related to the device, but just controls in the bigger view of your application. And you have the plugins that are responsible to execute that device code. So basically here you have GPU plugins, and we added the OMPC plugin. So the OMPC plugin is basically an MPI plugin that where your device becomes the MPI processes. So let's say you wrote an application for OpenMP Cluster and you run using MPI run to run across a cluster. You have something like that. You have a head node controlling your application and running basically the diagnostic layer and generating tasks that's going to be offloaded to the workers in your cluster. So these tasks were executing on the workers, and the idea of OMPC is to offload CPU tasks. So the project was born on running MPI processes executing CPU tasks. So you could not achieve anymore, could not compile anymore your OpenMP target codes for other architectures than the CPU architecture, the x86-64 architecture. But you could still use GPUs, for example, calling heap calls inside the CPU function, or calling CUDA calls inside the CPU function. But what changes in the code while using OMPC compared to the original OpenMP offloading? Nothing. That's basically the same. So the difference is that we always compile this for the x86-64 architecture, and you run the program using MPI run. So the standard way you use a distributed application. So, but as I said before, our targets, so our functions are always compiled for CPUs, but there is nothing blocking you to call heap here, for example, to use AMD GPUs, or call CUDA here to use NVIDIA GPUs. And another very interesting thing about OMC is that this is the code that you can run on your laptop. If you have MPI installed, you can run MPI processes in a single node, no problem. And it's gonna offload and thinks of MPI processes as your device. And you can take this same code without changing anything and run on HPC cluster with several nodes. So that is all this abstraction of the distributed computing on the code that user gonna write. So it basically comes for free. Speaking about the FPGA, OMC FPGA, we basically adding a plugin to the side of the OMC plugin. So they are kind of integrated. So you can use FPGA plugin to offload to FPGAs. And together with the OMC, we can use both plugins to offloading to FPGAs in a distributed environment. So there are a few works that try to do this with OpenMP, and they try to use compile the code here, for example, to the FPGA. But we strongly believe that this is only adding another layer of limitations, because we already have HLS, that's basically high-level coding for FPGAs. So you add another layer that you have to translate that code to HLS to then compile using bytes, for example. We think that you are only adding limitations there for not very much effort in the programming of these kernels. So we, instead of having the binaries compiled during the program compile, we read the FPGA binaries and put in the boards during the execution. So and this brings a few other improvements that I will talk soon. But the idea is that on the runtime, we read the FPGA binaries we have. So you can use FPGA binaries that are already built. You can just go to another repository and take a kernel there, build for your for the FPGAs you haven't used together using our framework. So it's simple as that. You have a program that uses a matrix multiplication, and you have a equivalent matrix multiplication kernel on a FPGA binary. You can use that. The execution flow is about the same thing, so it does not change anything. And about the code, it's almost the same thing. So you can see that there is no mention about FPGAs here. The only thing that we add to say that we want to use a kernel on the FPGA instead of the CPU is these two first lines. So the first is basically the prototype of your kernel on the FPGA, and the second is telling the OMP that you have that function as a variant for the following declaration, that is array sum, whenever you match the architectural view. So basically, this is the only thing that you need to say, that whenever we have array sum in the code, instead of executing array sum, we're gonna execute the FPGA kernel. So it takes much more. It's much more easier for you to say that I want to use FPGA kernel here instead of the CPU kernel without changing the code, and much more easier for you to switch between your kernel on the FPGA that's here and your CPU kernel, or even switch between kernels in the FPGA. You just need to change the declared variant. So how it works, we made the CLang, that is the compiler under the OpenMP compiler, understand that whenever we have the architectural view, this is declared variant for this, we pass this symbol to the task argument. So the FPGA plugin understands that this is the name of the kernel we want to execute instead of the CPU function. And to make this condition true, we basically say that when compiling the programming, we use these of FOPMP targets of view. The OpenMP offloading, we always need to use of OpenMP target. For the regular OMPC, we also use x8664 here, but here we use LView, and the code the compiler understands that we are talking about FPGAs here. And whenever there is a call to array sign the code, we use the FPGA kernel instead. So it's much easier to just plug in your kernels into the application. So a bit about the internals of this FPGA plugin. So right now it focuses on the device workflows. So we are talking about software controllable kernels, basically kernels that you can control through the XRT native API. In fact, that the XRT native API is what we use inside the plugin. But we still not supporting the user controllable kernels and free run kernels that are kernels that are already running or you control through the register in the kernels. And we are working with the buffered type of kernels that we have buffers among the kernels that you can use. Streaming, we are working on this right now. So you may expect this really soon. And this is basically implemented on the LLVM 15 and using XRT to that version of XRT or higher. That's basically the tools of 2022.1 or higher. And another thing that we always do with OMPC is make this available in containers. So brings much more, it's much more easier to use. So if the container is compatible to the version you have in the server of XRT, for example, you can use containers to just compile your code and then run your code. So the last thing about the plugin is how we use the XLB files, right? So by default, if you have an application in a folder in your server and you put an XLB file to the side of the application binary, it's gonna use if that's compatible to the FPGAs you have in the system and so on. But you can, and if it's to the side, you don't have to do anything, but you can configure a bitstream for every FPGA to use. So if you use this environment variable passing the path to the X7 file, it's gonna search in the path to configure each bitstream in your system to use that each FPGA in your system to use that bitstream. Or you can do a descriptor file. That's basically a file where each line is a path to a different bitstream for the FPGA. So you can configure a set of FPGAs in your system to run one Excel bin file and a set of other FPGAs to run another set of another Excel bin file. So this is something that our framework provides that other works that try to do OpenMP with FPGAs that not provide. So here you can have this flexible way to set which FPGA executing things. And you don't have to worry this on the code because you just generate your tasks and your target tasks there. And the runtime will take care of scheduling to the right FPGA that can execute that kernel or not. So one thing that's important here is that we are speaking about HPC, distributed environments, so we have to think about communication. So Marius just did a complete talk on communication right now, and basically the default communication approach for OMC with FPGAs is using MPI. So you have the staging. So you have to move the data from the FPGA to the RAN to the network and then to the other FPGAs. So we wanted to accelerate this and see what we could gain. So we integrated Echo it's very nice that Marius did his talk on top of echo, so I don't have to explain echo here. So basically, if you have strings that have echo inside, you gain echo for free. So basically, you don't have to worry anything on the application to say, I want to move this using echo or not. If the echo is available there, the plugin will configure, and whenever we have movement between two FPGAs, we're going to use echo, directly moving the data between FPGAs, avoiding the staging. And to account that, we did a experiment on the ETH cluster that's part of the AMD HACC clusters. We tested here 9 FPGAs on 9 different nodes, and we tested 4 megabyte buffers. And we use a synthetic benchmark that's called TaskBench. So I implemented TaskBench for FPGAs. And basically, we evaluate 3 types of graphs that are different in terms of communication. Sorry. So you have a light communication pattern, a medium communication pattern, and a high communication pattern here. And here we have the results for each one of those. And here we fixed the buffer size, and we just moving the computation each task can do. So we can go from more communication bounded to more computation bounded in the axis here, and in these roofline models here we have in the y-axis the efficiency, right, with respect to the best performance, which means that uh, we take the best we could performance that is communication, doing no communication, and we compare this using FFT, auto and 3 related to that one. So the basic key take we can bring from these graphs is that for the most communication bounded, we could use up to 41% more bandwidth compared to the baseline. And this and when we go more computation bounded, echo is never worse than the baseline. So if you can use the echo in your application, you should use, because it only brings improvements. And we want also to explore heterogeneity. So we want to bring this framework and try to do CPU plus GPU plus FPGA things. So we take an application to recolor image. So basically, we have a image that a few people don't see. So basically, here's an image with a 74. I can't see really, but this is what I see, the perception of a person that has CVD. And the recolor image is the resulting image that a person can see. So I can see that's a 74 here, but I can't see that's a 74 here. So this basically the tasks we have, and we try to using the declare variant, we try to set different scenarios here. For example, only using CPU, or using CPU plus GPUs, or using CPU plus FPGAs, or using both. All those 3 ideas here. So, and we did this on Unicamp cluster. This is experiment that use 1 FPGA, 1 GPU, and 1 node with CPU, but we don't have it here in Brazil. So we have a distributed application here for 1 node with CPU, 1 node with GPU, and 1 node of FPGA. And we tested also 1 hack box on the HACC cluster that has CPU, AMD CPUs, AMD GPUs, AMD FPGAs. And we can see by the results here that this is a more suited GPU application, but something that this idea of easing is changing what the scenarios you want, because you only change the variants here. We only set the variants to use GPU or FPGA, we can see that, for example, for a bigger image, CPU plus GPU is the way to go, but for a small image, maybe CPU plus FPGA plus GPU is the way to go. So this is a very simple way to test different scenarios that the framework brings. And another thing about this is the same code that we execute in Unicamp cluster, the same code we execute here. The only thing that's changed is that we have a CUDA for the GPUs here, and we have a heap for the GPUs here. Another thing that this framework brings is the profiling. So you can profile and you can extract information. So I don't have a lot of time, so I'm gonna go fast on this. But you can see for your scenarios how your approach is going. For example, CPU plus FPGA for bigger images, we can see that FPGA and communication is becoming the bottlenecks here, while using this tree, only the communication is becoming the bottlenecks. So you can easily get information to see to evaluate your approach. And finally, for this code, we also had the Halstead Metrics. This basically for the FPGA part. So we compared here for the serial application. Actually, it's not the serial application; it's the OpenMP application. OpenMP only, so CPU application. And compared to the regular way to implement MPI distributed using FPGA acceleration and the reduced stack that's using our framework, and we found out that we would reduce 45% the efforts to code. So basically, is reducing for 41 hours to 22 hours to implement that code. So a summary here, OMC FPGA brings the reduced to effort to integrate FPGA accelerator into applications, abstract the concepts of distributed environments, automatically use echo when it's available, and provides a nice validation mechanism through the variants. So you have your CPU code working and you have a FPGA kernel, you can just 2 lines of code, you say, I want to use that kernel on FPGA and test if that works or not. And basically, on the experiment, we see 45 reduction on the efforts to implement on the CVD application, 41.5% bandwidth utilization increase using echo, among other things. So there is more information on the paper. What's ahead? I'm gonna go quickly on this. So we are doing both OMPC and OMC FPGA to LLVM19. We believe this gonna do a smoother integration. And on the FPGA part, I would like to call attention for data streaming. So we think this is very important for FPGAs. So we are bringing something that enable that streaming effortless for the developer. So the code would not change. We would extract information from the XLB files with the plugins to see where are the streaming connections and infer some information of the streaming part, the size of the data you're transferring using strings, and we modify the dependencies during the runtime to enable kernels to string in the same FPGA or kernels to string in different FPGAs through some kind of network IP. With that, these are some acknowledgements for the funding agencies and also HACC and the research labs in Ireland. Some useful links, you can see this on the presentation after. That's the paper for the OMC and the paper we just published for OMC plus FPGA. And with that, I finished my presentation. Thank you for the attention.